want to just say what an honor it is for me to be here for this occasion, honoring Howard. But I'm going to keep the time. I won't tell my Howard stories. But I do want to, so I'm just going to go right into it. Our first speaker is Tom Pashby on the present state of the philosophy of quantum mechanics 35 years later.
So, first thing I want to say is we have failed to thank Eric. And Eric was really the driving force behind this conference. And unknown to me, we managed to organise the conference on his birthday. It's in fact Eric's birthday today, so happy birthday. So, about a month ago, I decided that it was a terrible idea to have committed to giving a talk at this conference and also be organising it. But it was decided that it was too late for me to pull out there. And so what I did is I thought, well, I'll write out a script. That way I definitely won't be up late the night before finishing my slides. Unfortunately, last night I decided that what I desperately needed were some slides. I was up early this morning doing some slides. Yeah, so this is kind of a new experience to me, sort of writing a written paper to be spoken aloud, so we can see how it goes. Eric said earlier that Howard Stein's papers are dense and rewarding, and I kind of think of that, you know, like cold rice pudding. Not that appealing, but you tuck in pretty great. But I worry that this is going to be sort of dense and unrewarding, more like cold congealed lard. So hopefully rice pudding, so we'll see. Anyway, sorry, on with the talk. So my subject is Stein's work on the interpretation of quantum mechanics. And I think unusually for a topic on which he wrote, and I may be wrong here, but I could find little in the way of obvious influence of the three papers that I'm principally concerned with here. So there's 1970, Is There a Problem of Interpreting Quantum Mechanics? Then the long paper, The Conceptual Structure of Quantum Mechanics. And then the paper with my title, On the Present State of the Philosophy of Quantum Mathematics. So this is the 50th anniversary of Newtonian space-time. It's the 35th anniversary of On the Present State of Philosophy of Quantum Mechanics. But despite that sort of lack of evidence of influence, I mean, I take myself to have been genuinely influenced by reading Stein here, and yet I don't think I've managed to refer to him myself. So perhaps that is not evidence of a lack of influence per se. And I first read Stein on quantum mechanics at the suggestion of Eric, I should say, just before I started my dissertation work at Pitt, so a few years ago now. So it's been an interesting experience as a sometime historian myself to read those papers again and try and reflect on how that influence was actually felt in my case. And reading Stein again a few years on, I found myself in the intervening years to have reached somewhat different conclusions from his. But I think the way that I came to them was clearly informed by his point of view. So today I'm going to try to enter into conversation with the version of Stein that I find in these papers. So in this paper, with my title, Stein is concerned with an analogy between the 19th century ether theories and the logic of eventualities, which is what he calls the lattice of projections, essentially. In either case, Stein claims, there was clearly quite positive knowledge about the structure in question. So on the side of the ether, it was the doctrine the structure in question is that of a connected material system, according to the classical wave theory of light, some sort of elastic medium, in the latter part of the 19th century, with the advent and the eventual triumph of Maxwell's theory, the ether, now not merely luminiferous but electromagnetic, had to have a still more complicated constitution, and what that internal constitution was appeared to many of the great physicists of the time to be one of the truly fundamental problems of science. And then, on the side of quantum mechanics, the larger doctrine is that propounded first by von Neumann, or some modification thereof, that either all or at least some commuting sets of projections represent sets of possible events, i.e. outcomes of possible experiments in a given physical system. More precisely, each single such set of commuting projections represents a set of possible outcomes of a single experiment. So those are the two sides of the analogy. Now, returning to the 19th century, it would be easy to suppose, if you hadn't read Stein's work, that the detailed investigations of the material constitution of the ether by physicists were simply a waste of time. You know, what could they have possibly learned about a non-existent entity? But of course, this is not at all Stein's view. While he criticizes the mechanical ether models of William Thomson, later Kelvin, as, quote, uniformly devoid of any significant connection with problematic phenomena of optics or electromagnetism, he presents as conspicuous instances on the, quote, honor roll of theorists whose ethereal speculations did lead to classification of phenomena and did serve to advance understanding of phenomena, Young and Fresnel, Maxwell, Helmholtz, Fitzgerald, Lorentz, Hertz. And on the contrary, Stein convicts Poincaré of the error of not taking the existence of the ether seriously enough. So according to Stein, Poincaré's dismissal of the ether as a fiction led him to discount the notion that the electromagnetic field might possess what he thought of as genuinely dynamical attributes, momentum, for example, as itself a harmless fiction, but without real significance for physical understanding. The brief moral I preach from this is that dismissive instrumentalism, as opposed to what I have called sophisticated instrumentalism, which we heard something about this morning, can be an impediment to the advancement of knowledge. And of course, for Stein, as we've heard, there's no reason to prefer a reasonable, tempered realism over a sophisticated instrumentalism. So he says here, the legitimate, as opposed to merely ideological claims of realism, and those of a sophisticated instrumentalism converge and consist effectively in the demand that theories and the questions they give rise to be taken seriously on their own terms and not dismissed as something mere. And now moving back to the side of quantum mechanics, the import of this analogy is that there is good reason to believe that our understanding of the physical significance of the algebra of projections is appreciably less than our larger doctrine implies, just as in the late 19th century physicists knew less about the ether than their larger doctrine implied. To press the point, I consider the attainment of a more coherent understanding of the physical meaning of this algebra to be one of the deep unsolved problems in physics today. So it's precisely toward this end that my talk is directed. So today I'm going to outline, sketch a positive account of the physical meaning of the algebra of projections, called elsewhere by Stein the logic of eventualities, and this is nothing other than the lattice of projections I referred to earlier. So my account will lean heavily on the idea that the meaning of projections is intimately tied up with the interpretation of experimental outcomes as physical events. What I mean by that is as concrete happenings located in time and space. Where this departs most strongly from Stein's account of quantum mechanics is in my reinterpretation of the propositional content of the lattice of projections, to de-emphasize the idea that projections correspond to properties or attributes of quantum systems. But Stein himself, in surveying John S. Bell's work, asserts that it has no means been proved that it is really correct to regard the projections of von Neumann as literally representing propositions about all possible properties of a quantum system. So he is, I take it, open to this idea. And a sort of more recent formulation of this idea, which I aim to endorse. I want to deny that there's anything physical that realizes such properties. Has been formulated by Potowski, calls it the second dogma of quantum mechanics. And here's a formulation from a paper of Jeff Boo and Potowski. So this is the dogma that they suggest we reject, that the quantum pure state is assumed to have an ontological significance analogous to the ontological significance of the classical pure state as the truth maker for propositions about the occurrence and non-occurrence of events. So that's the dogma that I would like to deny, but I don't want to endorse their rejection of the first dogma, which is the idea that an interpretation should avoid talk of measurement. And I'll hopefully have time to say something about that later. So returning to Stein's historical analogy, here's roughly how I see it working as a sort of positive analogy. So this is the sort of big picture. In the 19th century, physicists were trying to characterize the bearer of electromagnetic properties. What they eventually concluded is that the electromagnetic field is self-subsisting. It requires no underlying substrate to realize its dynamical properties. Now, if this seduction by substance is the core of the story of the ether, the analogy to 20th century quantum mechanics, I claim, is that 20th century physicists and philosophers of physics became seduced by the idea that quantum properties were realized in some underlying substrate, some sort of micro world, if you like, subject to the same understanding as the macro world, and that quantum theory aims at describing that world. So I suggest that the moral we're perhaps still waiting to learn in this case is the same, that no substantial property-bearing entity is required to realize the dynamics of the quantum state. So my contention is that focusing on the lattice of projections under the standard logical interpretation is a mistake along these lines. On my view, quantum mechanics is a probabilistic calculus first and a propositional calculus second. So I regard the proper subject of quantum mechanical propositions to be objective chances for the occurrence of possible and actual events, rather than the possession of potential properties or attributes of quantum systems. Nonetheless, I see Stein's approach to quantum theory as being broadly compatible with this adjustment. So I think there's a sense in which Stein, rather than giving an interpretation of quantum mechanics in Van Fraasen's sense of saying what the theory must be like, what the world must be like if the theory were true, I see Stein's concern as more that of giving an account of the positive knowledge that we should take ourselves to have in virtue of the successful empirical applications of the quantum formalism. So here, with Stein, I'd like to turn to a detailed consideration of our grounds for believing physical theory, that is, experiments. So the striking claim made by Stein in this 1970 paper is...
Your thing isn't coming on.
Yeah, I'm getting to it.
Okay.
Is quantum mechanics poses no special problems of an epistemological kind. And he later cashed that out as follows. Insofar as quantum mechanics provides a fundamental account of the existence and properties of ordinary bodies, it must follow that the theory contains, in principle, an account of every experiment. And the problem of interpretation would seem, therefore, in principle, to be solved intrinsically and definitively. This underlies the statement, quantum mechanics poses no special problem of an epistemological kind. Now, I should emphasize that it's not that no problems remain. He doesn't downplay the remaining problems, but he says that they are properly characterized as physical or metaphysical rather than epistemological. Now, presumably the absence of special epistemological problems means that this is the kind of knowledge that any kind of physical theory should be expected to furnish. And that amounts roughly to something like a claim of empirical adequacy cashed out in terms of experiments. And in the quote I just gave, this seems to follow from the claim that the theory describes the objects of common experience. But why should experimental knowledge suffice? Shouldn't we share John Bell's concern that we must set our sights higher than knowledge concerning mere piddling laboratory operations? So here I think Stein's later notion of the schematicized observer, which we've already heard a little bit about, we'll hear much more in a minute, I think is relevant here. So, as we've heard, Stein later introduced a further criterion for interpreting a physical theory, that it should allow for, quote, the schematic representation of observers' experiments and observations. Now, concerning epistemology, Stein expressed the sentiment as, quote, the simple remark that our understanding of our own relation to the world is mediated by our ability to place ourselves, however schematically, within our conception of the course of nature. But then, and this is almost at the conclusion of the paper, well, it's in the conclusion of the paper, nearly the last paragraph, one would like to say a similar thing about quantum mechanics, particularly in respect to what it tells us about the structure of causation and our intuitions of causation. But this we cannot do. In this theory, we just do not know how to schematize the observer and the observation. This is a quick way to characterize what I regard as still the basic unsolved philosophical problem of interpreting the theory. So here's how I take this point, at least. So in the standard von Neumann-Mackey formulation of quantum mechanics, discussed extensively by Stein in these papers I referred to earlier, it is more natural to consider the theory, I think, as providing a schema for what an observer can do according to the theory and what they might expect to see. But it does not say what they are according to the theory. In Mackey's quantum formalism of observables understood as experimental questions, there is a latent tendency to regard the observer as somehow having an extra physical capacity to choose both which questions to ask of a quantum system and when. But here I note that various competing interpretations of quantum mechanics do provide a place for the observer, and apparently an answer to the question of what she is. For example, if one introduces a primitive ontology or beable, in Bell's terms, say definite particle positions in Bohm's theory, then the observer schema, it seems to me, is just going to be given in terms of that primitive ontology, or alternatively, in the currently fashionable Everett interpretation, one attempts to place the observer into the quantum state, embracing the dizzying multiplicity that results. Now these are, I take it, examples of what Stein characterized, and here I definitely quote, as glib and inadequate pseudo-solutions, end quote, to the epistemological, physical, and metaphysical problems raised by quantum mechanics. And I agree that we should resist the Bohmian rallying cry, which certainly not back to Kant, but perhaps back to Boscovich, or the Everettians, the quantum state taken literally. In contrast, I think Stein sought what Laura Ritchie has called a pristine interpretation of quantum mechanics, one that does not add nor take away from von Neumann's formalism of probabilities and projections. So turning to this account of the formalism, Stein's discussion begins as follows. And I should note that he immediately calls this already oversimplified and misleading, but here it is. The constitution of a system must be supposed to entail for it a definite complement of testable attributes, each accessible to empirical determination. by the help in general of a suitable physical apparatus which we bring in to interact with the system in order to evoke the manifestation of one or more of these attributes. A test of a single attribute is in effect a yes or no question put to the system. This is Mackey's interpretation as experimental questions. It would be misleading to think of these attributes as properties of a system in the ordinary logical sense of property. Instead, on the domain of all possible conditions of the system, they are best conceived as partial or conditional properties, functions into the set of truth values defined on possibly proper subsets of that domain. And then he goes on. In probability theory, the subjects to which probabilities are ascribed are ordinarily referred to as events. To suggest the potential character of our attributes, which are phantoms and limbo until they are called forth by suitable test procedures, I shall prefer to use the word eventuality, and shall say that a statistical state assigns a probability to each eventuality of the system. I shall speak of an experiment as realizing an eventuality. If the experiment can be regarded as a test for that eventuality, thus the experiment can prove affirmative or negative, and the probability is to be construed as the conditional probability of an affirmative realization on the hypothesis that an experiment realizing the eventuality in question is performed. So this interpretation of the probabilities supplied by quantum mechanics as ultimately conditional probabilities is one that I heartily endorse. And if these probabilities are conditioned on the realization of some eventuality, then from the axioms of probability theory, there must be some event that gets assigned probability 1, which can be understood as representing not the specific outcome of the experiment, but the fact that the experiment takes place. And what I want to resist is the identification of Stein's eventualities with projections, which I take to be somewhat tied to the suggestion that they might represent testable properties or attributes of some object, that is, the quantum system. So let me try and explain. I'm already a bit behind in time, so let's see how much you get through. So, as I've said, what Stein calls the logic of eventualities corresponds to the lattice of projections under the standard logical interpretation of Birkhoff and von Neumann. So the self-adjoint projections are in one-to-one correspondence with the closed subspaces of the Hilbert space of the system. Considered together, these form an orthomodular lattice whose elements are partially ordered by subspace inclusion. Now, this partial order is amenable to a logical interpretation as implication. Linear sums, set products, orthocomplementation are interpretable as disjunction, conjunction, negation. And under this logical interpretation, we find that maximally specific propositions correspond to the atoms of a Boolean sublattice, which in Hilbert space corresponds, the sublattice that is, to a maximal commuting subalgebra of bounded operators, and thus a self-adjoint operator, and therefore a projection valued measure, or PVM. So this is a lot of jargon, but hopefully it will have some payoff. So this leads naturally to the idea that the condition under which these probabilities apply, the ones generated by this projection valued measure, corresponds to the top element of this Boolean sublattice, in the sense that the realization of any eventuality of that Boolean lattice also realizes the eventuality corresponding to the top element. But this is somewhat puzzling, I think, because in every case, this top element corresponds not to a projection onto a proper subspace, but to the identity, the whole space. Is the same event then to be realized in every experiment? So here I turn to the approach of Michael Dixon to understanding symmetries in quantum theory in terms of quantum reference frames. So using the now standard terminology, an observable is positive operator valued measure, or PIVM. The PVMs mentioned previously are also POVMs. What is such a thing? Well, it's a map from a Borel sigma algebra to the algebra of bounded operators on a Hilbert space, having certain properties that secure the interpretation of its image in terms of probabilities. It's just the sort of gadget you need to get probabilities out as expectation values through the Born rule. The question of empirical significance raised by Dixon concerns the domain of this map, that is, the elements of the sigma algebra, here interpreted as events to which probabilities are to be assigned. Now, on the other hand, I take it that questions about Stein's eventualities are concerned with what lies in the range of this map, namely these projectors, the projectors onto the subspaces of the Hilbert space of the system. Now, what does Dixon have to say? Well, following a survey of Mackey's systems of imprimitivity, which is also a subject of Stein's papers, in their applications to POVMs, Dixon declares the basic point is that the reference frame dependent observables may be uniquely characterized up to trivial transformations such as scaling of length, global unitary transformations, by the invariances and covariances they obey with respect to some appropriate symmetry groups. In this sense, the very meaning of position, momentum, and so on is partially given by these invariances. You know, this is a view you can find in the book of Yauk. I can't say that, but you know, maybe you know what I mean.
That's right.
There we go. Thanks. So Dixon continues, concerning the empirical and observational significance of such symmetries, the basic proposal here is that reference frames describe the world as witnessed by some observer and ultimately some human being, so shades of this schematicized observer. The suggestion coming from various 19th century philosophers of geometry, such as Helmholtz, Poincaré, is that such transformations are connected to experience by the physiological kinesthetic experience of undergoing the change from observing one reference frame to observing another. No, not the end of that. So, in answer to my question, well, is the same event realized in every experiment? Dixon would suggest, I think, that it is not what is mapped to that matters, but rather the behavior of those maps under these physically significant symmetries. And therefore, the physical character of the unit events on which the realization of an eventuality is conditioned depends on our interpretation of the domain of these mappings, the original sigma algebra from which they are mapped. Ultimately, though, Dixon appears to favour an association of these sigma algebras with coordinate systems and of the parameterized families of spatial translations, rotations, boosts, times translations, with motions of the observer herself, which she may associate with particular kinds of experiences. Now, I don't doubt that such an association with capacities for motion of the observer can give empirical content to those parameters. But first, I just want to note that there's no need to restrict ourselves to transformations of the observer. We could also associate such parameters with our capacities, for example, to set the system into motion relative to the laboratory and even rest, under a natural interpretation of the Schrödinger equation of unitary evolution as an active time translation of the system. And of course, these active transformations can also be associated with experience, just not necessarily a motion of the observer. But my second and I think more telling worry about Dixon's quantum reference frames is that any coordination of transformations with experience fails to give empirical content to the events which are, according to von Neumann's doctrine, those things that we associate with experimental outcomes. So how are the elements of the domain of an observable, the domain of this map, the POVM, how are those to be related to experience? Well, these elements, I claim, derive their empirical content from an association with possible outcomes of an experiment, where here I mean an outcome taken sort of concretely, a registration event actually observed in the lab. These are the raw data of experience constituting the result of an experiment. And so that's what these must be probabilities for, to give them meaning empirically. So ultimately, I claim, reference to experience is to be made, so to paraphrase Schrödinger, in terms of the appearance of a dot or the click of a detector at some place at a time. And that's what I mean by an outcome of an experiment as experienced. So I propose to reject the characterization of eventualities in terms of Mackey's experimental questions, that is, yes or no questions put to the system by the experimenter at a time of their choice. Instead, I contend that eventualities are not to be regarded as potential properties or attributes of the system under test, but instead tentatively approached by the various distinguishable, mutually exclusive outcomes of an experiment characterized as a whole. And these outcomes are what I want to identify with registration events, both potential and actual. So, to make two brief remarks about why we should reject the view of eventualities as potential attributes or properties. So first, to what object do these properties belong? An interpretation according to which particles or quantum systems come to have properties in the course of an experiment is committed to the view that ultimately a particle or a quantum system is a subject to which a property could belong. And it's precisely this metaphysical presupposition that I hold to be analogous to the idea of the ether as this substantial bearer of electromagnetic properties. And the second remark is that the unitary dynamics of the quantum state are just really incompatible with the possession of any given property for a non-zero duration of time. And this is a result that's not that hard to show. It's related to the phenomenon of so-called instantaneous wave packet spreading. So I won't give that argument here. You can find it in my dissertation. In a recent article, David Wallace has made essentially the same point. So what is the alternative? Well, rejecting Clapp's, Wallace continues to give the quantum state a substantial interpretation, I would claim, and explains the apparent exclusivity of experimental outcomes by a dynamically enforced multiplicity of the observer. In contrast, I propose to follow the suggestion of Bertrand Russell and Alfred North Whitehead, made now over 100 years ago, to extend the rejection of the ether to a wholesale rejection of the need for any permanent substance to underlie the changing appearances of the physical objects of experience. Rather, it was appearances themselves that were to be reified as events for Russell and Whitehead, envisioned as concrete particulars that are the relator of spatio-temporal relations and thus constitute spacetime. Now, looking at more recent work in the foundations of physics, I take John Bell's flash ontology interpretation of the GRW dynamical collapse theory to be sympathetic to this kind of thing. So here's the quote. Maybe I'll just sort of skip this. So we have these real events in the world. A piece of matter then is a galaxy of such events. As a schematic psychophysical parallelism, we can suppose that our personal experience is more or less directly of events, in particular pieces of matter, that is, our brains, which events are in turn correlated with events in our bodies as a whole, and they in turn with events in the outer world. And you can find very, very similar things being said in Bertrand Russell's analysis of matter. So, what of von Neumann's doctrine on this view? So, rather than following GRW and introducing a primitive ontology of flashes by sort of enforcing this stochastic term which we add to the Schrödinger equation, I simply favour a reinterpretation of projections as corresponding not to propositions about the possession of properties at a time, but to propositions about the occurrence of an event at that time. So then, what is realised in an experiment is not a property of a particle, but an event. And here I turn to another physicist who has written in sympathetic terms. So this is Rudolf Haag. What do we detect? The presence of a particle or the occurrence of a microscopic event? We must decide for the latter. The standard use of the term observable does not really correspond to the needs of collision theory and particle physics. We do not measure a property of a microscopic system characterized by a spectral projector of a self-joint operator. Rather, we are interested in the detection of a microscopic event. The first task is to characterize the mutually exclusive alternatives for such event. So I'm going to very much depart from his approach to doing this, but the sentiment is one I wholeheartedly endorse. So returning to my earlier discussion, the realization of an eventuality on which an assignment of probabilities is conditioned, what I call the unit event, now corresponds to the certain occurrence of a particular kind of event, but, and this is vital, not an event that occurs at any particular time. For example, we might condition on the appearance of a dot on a luminescent screen somewhere on that screen at some time. So, to illustrate with a simple case, here's our state preparation device. It's going to emit electrons prepared in some pure state. And here's our apparatus, a double slit. Here's our registration device, a screen. So the experimental results here concern expectation values. So we prepare many identical systems in the same state many times. We get this build-up of dots reflecting some kind of interference pattern, and that's how we obtain our statistical averages to compare with the expectation values given to us by the theory. But what do we see in some given run? Well, a single dot appears on the screen. And this suggests that the distinguishable, mutually exclusive experimental outcomes correspond to locations on the screen. And the spatial symmetries of the screen itself suggest a mathematical representation of these eventualities based on the Euclidean plane. Now, the subsets of the plane form a Boolean algebra, the lattice, elements of which are apt for interpretation as signs of eventualities. How? Well, I'm going to again try and pass over some subtleties. Well, we set up an association of measurable subsets of the plane with projection operators on the Hilbert space of the system, such that the expectation values of these projectors in a given state return the correct probability through the Born rule. And if we introduce temporal evolution in either the Heisenberg or the Schrödinger pictures, we then obtain a time-indexed family of expectation values interpretable as probabilities. And here I'm thinking we've got some definite region of the screen that gives us an expectation value that we can interpret as a probability, apply time evolution, and we get a temporally indexed family of those expectations. Now, what are those probabilities for? According to Stein, these are probabilities for the realization of a position eventuality of the particle. But the times are being distinguished here. What is the probability for realization of such an eventuality at a given time, or even a time interval? So my proposal, that I've made in some detail elsewhere, is that we treat the time-indexed expectation value of a projection operator assigned to some region of the screen as a probability density, over which we integrate to obtain a probability for the occurrence of the event to which the projection corresponds during that duration. And as I've shown, this probability is properly normalized when conditioned on the event that the experiment has an outcome at some unknown time somewhere on that screen. And I think this approach is required even when considering time-independent probabilities. So if we think of the experiment as a whole as answering an experimental question, well, we could take it to be answering the question, will the dot appear in the left or right-hand sides of the screen? And according to our association of regions with projections, yes, to the left and right-hand side of the screen, there correspond orthogonal projections. But these projections have time-indexed expectation values, which, under the Born rule, provide probabilities that sum to 1 at any given time. Now, taking those unit events to correspond to the appearance of that dot at that time suggests that, well, there's probability 1 for the dot to appear at every time, which is surely not what we see. However, when we interpret those expectations as a probability density, we integrate over time interval, we obtain a probability for occurrence at some time during that interval. And thus we obtain probabilities by integrating up all times of the experiment for the left or the right, irrespective of the time at which that dot appears. And just to sort of illustrate what I mean by time, I don't mean an absolute time, I mean a relative time. So the idea is we can control the time of emission by, say, pulsed laser. So we know roughly when the particle was emitted, and then we can record the time of arrival, do it again, we won't find exactly the same time. And of course it will arrive most likely in a different place. But in so doing, we find that the proposition that the dot appears in the left, say half of the screen, corresponds not to a projection but a positive operator. And due to a result often called Pauli's theorem, this is provably a general characteristic of the POVMs, the observables, that provide probabilities for these temporally located events. Now, the use of positive operators that demonstrably fail to be projections would appear to suggest a more radical break with von Neumann's doctrine of projections than perhaps I've sort of signalled. But this appearance is illusory. So the sort of considerations surveyed by Stein in '82 that informed his attitude that the doctrine of von Neumann is of deep philosophical significance have to do with mathematical results. Von Neumann's spectral theorem that secures the relationship of unbounded self-adjoint operators with projections and thus subspaces of the Hilbert space. Gleason's theorem, which shows that probability assignments on those projections must correspond to von Neumann's density operators and vice versa. The Stone-von Neumann theorem and Stone theorem, Mackey's imprimitivity theorem, which has to do with representation of symmetry, so on and so on. Anyway, these considerations lead Stein to announce, I should be profoundly surprised, I might almost say shocked at nature's irresponsibility, if so striking a system of connections turned out to be really fortuitous. So there's a tension here. And I think the expansion of the logic of eventualities to include positive operators that are not projections, and I mean here what's often known as the algebra of effects, I think may occasion such surprise. But it's really a conservative move. This algebra strictly includes the lattice of projections. So the last thing I'll do is just try and explain why. So I'll skip a whole bunch of stuff. So the spectral theorem demonstrates the existence of a unique measure over the spectrum of a self-adjoint operator, called appropriately the spectral measure, integration over which allows the functions of the operator to be expressed as functions of the integrands. When that function is the identity, we obtain a resolution of the identity for one parameter family of projection operators that can be integrated up to obtain a projection value measure, PVM. The spectral measure then can simply be expressed in terms of the unique projection value that it defines. Now, the modification required to accommodate the algebra of effects was apparently first noticed in the 1940s by Naimark. The key observation was that a symmetric operator without self-adjoint extensions can nonetheless play the role of a self-adjoint operator in the spectral calculus, with the distinction that this generalized spectral measure must now be expressed in terms of positive operators that are not projections. But, as I've said, gratuitously, the positive operator value measures that result from this generalization turn out to be perfectly suited to the role of supplying probabilities. But you might ask, how can this be, given the tight connection of projections and probabilities announced by Gleason's theorem? Well, the answer is straightforward. By allowing probability distributions on this whole family of probability apt positive operators, the algebra of effects, which strictly includes, of course, the set of projections, one strengthens the premises of Gleason's theorem and obtains a proof that to a generalized probability assignment on the algebra of effects, there corresponds uniquely a density operator and vice versa. And remarkably, this result extends to a Hilbert space of 2 dimensions, a case excluded from the scope of Gleason's theorem. So what is the significance of these results? And there are others like them that would account for other results surveyed by Stein. Well, they remove the temptation for essentialism about the lattice of projections. Since this extended class of positive operator value measures play the same theoretical role as the restricted projection valued measures, and arguably better, an independent reason is required to pick out the projections alone as the appropriate objects of interpretation for a propositional calculus. Now, one could argue that, well, the projections still allow for a representation theorem, Gleason's theorem, and of course they're also involved in this weaker result concerning the algebra of effects. Sure, but then that's a move made not of necessity but of choice, and I think we're owed an account of in just what that significance lies. So unfortunately I have a whole lengthy second section that I will not go into, you'll be pleased to hear. But I would like to just say something, so I think it's so yeah, let's conclude this. So as I've said in the build-up to the talk, unfortunately I didn't get to go into this in a bit more detail. So my own view about Stein's analogy in the 82 paper is that no underlying substantial property-bearing entity is required to realize the dynamics of the quantum states, just as no underlying ethereal substrate is required to realize the dynamical properties of the electromagnetic field. Nonetheless, I hesitate to claim that the quantum state fails to refer, and I'm certainly not going to say here what I do take it to refer to. But I did say before that I depart from Bohm and Butowski in accepting this dogma, that we should try and prevent measurement from playing a fundamental conceptual role in an interpretation of quantum mechanics. So I see the task for someone who would reconcile a tempered realism with a sophisticated instrumentalism is somehow beginning with experience in the way I've suggested, making sort of realist content with the quantum state. And yeah, I really can't say any more about that, so I will conclude there. So thank you.